All right, so we've had our time in Theory Town. We've talked about normalization. We've spent some time working with descriptions of actual data, drawing ER diagrams. We've even converted those ER diagrams into create statements to make tables. And probably after, by now, the time you watch this, 2 exams, 2 assignments, and well into the second month of the course, a lot of people are probably wondering, when do we get to actually work with databases? And the answer is not yet. We have to talk about a bit more conceptual stuff. So we're entering a period of the course where it's not as straightforward to me how to turn it online in a sort of linear stream. So the way I would do lectures in person for this part of the course is a strange mixture of slides here and there, the live use of database software here and there, and the board. Because of the fact that when we're looking at one screen and I can only record a video with a certain resolution, because that's going to be a bit busy if I try and flip back and forth, and because you can always pull up extra windows, so you have the option of following along or whatever, what I think I'm going to do is record separate streams of videos. So I'll record videos for the slides, for the conceptual stuff. I'll record a couple of videos for the early bit of just explaining how to use the database clients, how to get into our system. And then I'll record some videos that sort of amount to the live coding part. So query design. How do we write queries? If you're given a question, what do you do to tackle that query? So we're actually now at the point of the course. If you take a look at Connex, you can see in the sidebar there are now instructions under the Books and Software tab for how to log into our database servers. There's a page called Databases you can take a look at, which gives the description of all the different data sets we have to work with. And so we are imminently going to begin writing lots of queries, and we're going to enter this period of the course where the questions you get are basically, here's a description of something, write a query, or here's a query, describe what this query is doing. And arguably, in terms of what people use out of databases, there are plenty of people that go out there and don't become database administrators or database designers. But pretty much everybody has to use some SQL at some point in their career. And so this is the part of the course that we're entering where it's the most transferable skill, I think. I don't want to discount the importance of the rest of the material, because arguably you can't learn to write good queries until you know about stuff like normalization. But we're entering the point where it's most likely every single person taking this course, if they go on in this business, will have to use some SQL at some point in the future. The first thing is, in an in-person lecture, I would typically put this slide up on a separate projector, and then run through my other slides elsewhere so people can see both. You might want to go to Connex and grab this presentation and then just pull up this one slide, because as I go through this, we're going to keep referring back to this schema, and I can't show it all in the same place. I'm also going to observe, if you didn't already take a look at this, this is a good time to go watch that Introduction to Basic SQL lecture that I recorded and posted in early May, because we're going to use little snippets of SQL. We're not going to use the advanced stuff at first, but we're going to use SQL up to and including the level of what we saw in that video without really going back over it from scratch. So go take a look at that if you didn't look at it already, or if it's been a while. We're going to spend most of this set of slides talking about a conceptual way of modeling what a query is. So, well, maybe we should define the word query first. I have a bunch of data. We know already from our discussion of stuff like normalization, this is a normalized schema. We know already that it is possible to extract lots of detail from this set of 3 discrete tables with things like joins, with the ability to search it, with the ability to take the columns that we want and read certain meaning into them. So I could, for example, compute the total price of an item in an order by multiplying the price per kilogram by the number of kilograms that were purchased, things like that. But we still have to figure out how do we formally state that? How do we tell the database that that's what we want? And it turns out that SQL as a language is what is called declarative. If you take a programming languages course at some point in your academic career, you will learn that there are families of languages, and the one that you're most likely familiar with is, broadly speaking, what's called the imperative family of languages, which is languages where you write a sequence of statements or commands or something, and we just run them from top to bottom. You're basically stating an action at each point, right? So x equals 5, y equals x plus 6, things like that. There are other styles of language. So you may know that the imperative family of languages is actually defined by the existence of things like assignment statements. And if you've seen things like functional programming, you might notice that they don't really have, functional languages don't focus so much on assignment statements and variables and states. There is this other category called declarative, where instead of programming by using the language to say what to do, you instead program, as we will with SQL, by explaining what you want. You describe your result. And that's ultimately what an SQL query is. An SQL query is a formal way of me being able to say things like, give me the total cost of everything purchased on June 16th. So I'm stating formally what my result is, and I'm then expecting the language, the database engine, to parse that, understand it, and figure out how to give me what I want, as opposed to what you're usually familiar with, which is listing the steps in a process, implementing an algorithm imperatively, one step at a time. I'm going to use bits of SQL in this lecture. As I said, this lecture won't introduce those. Those were introduced already. It just was a long time ago. What I want to talk about first is some review of some stuff that may have gotten buried because it's been a while. The first thing is, yeah, we like using tables to represent these things, and we even call them tables inside a database. But remember that this is a relation. We're working in the relational model. We have a normalized schema of relations. And that has implications because formally a relation, like the products table here, is a set. And it actually is a set of what we call tuples, which are ordered, okay, I can just draw an example here. So I've got one apple. So the product ID of apple is 1, its price is 3.5. And then I've got 2, and then pear, and then 4.0. And there's a bunch of other ones. I'll leave that as an exercise. So our relation is actually a set, and we know already that that's significant because that is what forbids us from having the same tuple in there twice because of the way that sets work. It is a set of these tuples, and a tuple is ordered. So it is significant that formally in a mathematical sense, so external to a database's course, just in a fundamental mathematical sense, if I look at these two tuples here, 1, apple, 3.5, and apple, 1, 3.5, these two things are distinct. And so we have this issue that we had to discuss earlier, which is, well, wait a minute. If I'm using the consistent ordering that ID comes before product, the name of the product comes before price, so that is to say, every tuple is being listed in this order, then why does it make much of a difference what order I use as long as I'm consistent? In the relational model, that's a bit of a headache. And the way that we work around that is when we describe a particular schema, so I apologize for scribbling all over these things. When we describe a particular schema, let's use the products table here, we've been writing it as the schema for relation is the relation's name, so products, and then its attributes in the order we choose to represent them. So ID, name, and price per kilogram. And we've decided that if we've described the relation that way, then we expect that whenever we see a tuple in the relation, the first thing in the tuple is ID, the second thing is name, and the third thing is price per kilogram. And that's fine. And it's worth considering that if we decided for some reason that we would rather name came first, ultimately, and we've already defined this, take a look at the earlier lectures if you want proof of that, but ultimately it's the same relation. If I just permute the elements, if I decide that name comes first and then ID and then price, as long as I say that in my relations schema, it's actually just the same relation. The ordering of columns, as long as it's consistent inside the representation of the relation, the ordering of columns is sort of irrelevant. And I only need to order the columns because a tuple fundamentally has to be an ordered thing. So what that means, and what this slide is ultimately getting at here, is that the ordering of columns isn't significant, and therefore we assume that we've chosen some column ordering for all of our relations and that's sort of fixed. There are lots of other ways of defining it. We could define some canonical form or something, but that's, for the most part, it's easier just to say, look, we've decided the order of columns for a relation, and that's it. And if we talk about two relations with the same set of columns, and or attributes, and we identify columns as the same if they have for example, the same name is one criteria we could use. If they have the same set of columns and once we arrange the columns into the same order, they have the same data, those two relations are equal. That is the interpretation of this paragraph here. So regardless of how I'm storing the columns, which column comes first in the way I'm storing it, if I have two relations with the same set of column names and the same data in each column, and once I rearrange the columns into the same order for both relations, each row is the same, then the two relations are equal. So first, a relation is a set. That's going to be a big deal. The reason it's a big deal is we want to define basically operations we can do on relations. I want to be able to say something like, here's a relation, like I would in SQL, select from this relation all rows that contain the name Raspberry. That is an operation on the set. It is a narrowing operation that specifically looks for one thing in the set. I could also ask for things like, give me every item whose price is greater than 4. And so that would be going through the set, searching through and choosing certain rows. I could also say, take this relation, give me a new relation with only the first two columns, ID and name. So just strip out that price per kilogram column. We've also seen, of course, I could do things like joins. So I want to define operations that use as their operands relations. The fact that a relation is a set is actually sort of nice because we already know some operations that we can do on sets. Now we're going to see that some of them aren't very helpful at first, but it's important to think about that. It's also important that despite the fact that database engines, including Postgres, the one that we're using, so I'll write it out, we're using a database server called, formerly it's called that. Typically people just call this Postgres. Basically because every database engine, it was common in a certain generation of databases for them to just have SQL mashed into their name somewhere, so we just ignore that because it's common to all database engine names. Even our database system, Postgres, does have some behavior that doesn't match up with the relational model perfectly. So, for example, it will let you, if you know what to do, it'll let you put the same row into a table twice to allow duplicates. You can, of course, make it prevent that. There is a way of doing that. But there are times when despite the behavior of the database in certain cases, the fact that we can treat relations as sets is beneficial because we can use those set operations. Whether or not they happen to be useful now is one thing, but we can use them. And so here's some examples of set operations. So these are operations we already know. You learned these in like Math 122 or something. So the reason why I had to go through that long diatribe about column ordering is that what I really want to do is just put that behind us, to say, look, we have relations. We'll assume that our ordering of columns is irrelevant, that if we have two relations with the same set of columns, that they are the same thing. So the way I've ordered the columns is irrelevant. So let's just not worry about that and talk about the relations as sets. So if I have two relations or sets, and I think about what can I normally do with sets, well, you have two sets, you can take the union, which if I have two relations and take their union, I'm asking for a new relation that contains all of the tuples in R and all of the tuples in S. But we know already that if I take the union of two sets S and T, the result is itself a set. And the same is true with relations because they're sets. R union S is a relation, which means all tuples in R and all tuples in S are put in, but if there are any tuples that happen to be in both, they don't appear twice. So there are no duplicates in the result of taking the union. Then I've got the intersection. R intersect S would be a relation containing all tuples that occur in both R and S, just like in the set version. R minus S, now some of you out there are looking at this and saying, minus, I don't know about drawing. So everybody agrees there is an operator called minus to find on sets. Some people use weird ones like R this, they use a funny looking sort of diagonal thing. I don't know about that. That's too many symbols for me. So I'm one of these people that just uses the regular minus sign. So R minus S is a relation containing everything in R minus everything in S. So all the tuples in R that do not appear in S. And then we have this one, R cross product S. So this is actually called Cartesian product formally. I'm going to call it cross product a lot, and you'll see why pretty quickly. It turns out that SQL has no use for the word Cartesian. You might also notice that Cartesian, strangely, the word Cartesian comes from Descartes, so it's named after a person. The Cartesian product is named after a human being with a proper noun as their name. But due to weird historical stuff, we never capitalize the C. One more reason to just call it the cross product to avoid confusion. So the cross product of two sets is this new set that is a bunch of ordered pairs, and order is significant here. So ordered pairs as opposed to unordered pairs means R cross S will guarantee me that the element of R comes first, whereas S cross R would have S comma R. So order is significant here. So R cross S, or R Cartesian product S, would be a collection of all possible ordered pairs where one element, the first one, is from R and the second element is from S. You can view this like writing two nested loops. You loop over every element of R, and then for each element of R, you loop over every element of S, and then emit the pair R comma S. So these four operations are free. We know that we're working with sets. We know that relations are sets. We can therefore do these four operations on relations. Now, what we might notice, though, is that these do not at all help us with the basic problems that we tend to want to solve, even at this stage. I want to ask questions like, give me all the products whose price is greater than 5. And these don't contain any consideration for that because they're general set operations. We might be working with, in Math 122 or something, sets of integers. So we don't have this ability to say, go in and look at the row and evaluate the specific column. But it's worth considering. We do have these operations. We can put them in our back pocket. So we need to define new operators. Union, intersection, minus, and cross product aren't enough. We need new operators, but they're still just set operators. They're specialized for this particular kind of set, a set containing a bunch of tuples. And I need to define them to be able to do basic things like pull out specific rows of a relation, to eliminate columns. So for example, give me the name of each of all the products. Don't give me the ID, don't give me the price. And we also want operators to do things like joins. So we're going to define this new set of operators. And I'm trying, you can tell, I'm trying real hard to couch this as an extension of our normal set operators. That's it. I'm not saying, this is going to be annoying algebra stuff as you'd expect from a lecture about relational algebra, but it's really important to me that we view this as just being more set operators, more specialized set operators, as opposed to a completely brand new thing. So we should generalize our view of the way sets work. So we'll start with these set theory operators, union and intersection, and we'll add on more and more as we need to add extra functionality to our ability to use relations and gather information from them. So then there's the question, why are we doing this? So why are we talking about set operations? Let's just get on with it and write SQL queries. Well, there are a couple of issues here. So one of them is, ultimately, SQL is just one language. The same way that Java is just one language and C is just one language. And it's important, and by now, of course, you know this, that obviously you don't want to get a degree in Java. You don't want to get a degree in C. And you especially don't want to leave a computer science program believing, as I'm sure none of you do, but believing that programming equals Java, or programming equals Python, or programming equals C. These are all just sort of imperfect ways of realizing what programming is theoretically. And the same is true of SQL. SQL is a language designed by people who made design decisions. They made them in the 70s in the vast majority of cases. There are some newer bits of SQL out there, but these design decisions may not have been good ones. And SQL syntax, as you may have noticed, is a bit weird. It doesn't really resemble most languages we're likely to have seen. And so we don't want to get this impression that all we can do with data is all we can describe in SQL. It's a sort of typical issue that human brains have with language. You might be familiar with this idea that whatever your first language is actually dictates a lot about your thought processes. And if you learn more languages, so my first language is English, for example. I don't actually know, besides C++ and SQL, I don't know any other human languages besides English. As far as I can tell, it's the case that if I learned more human languages, my thought processes would be different, and it's been observed that depending on which language people know first, the way they think is different, and language can often restrict how they can think. which is probably a consequence of the way that human brains have evolved. So that's a weird philosophical aside. It's important that we don't think about data processing as being SQL. SQL is one way that we achieve this. The same way that I don't view a car as being the same as transportation. There are lots of ways of traveling between 2 points. And if all we ever think about is driving a car, we end up with a pretty limited view of the world. And we end up thinking there's certain places we can't get to because there are no roads that go there. We need to be able to talk about processing data in its purest form, in the most abstract sense. And we'll see later, we'll wrap back around to this. We'll spend a long time in SQL world, but we'll see in July that actually without the ability to talk about relational algebra, we really have no idea what it means to run a query quickly. If we want to talk about how a database can be fast, how do we optimize our queries, we need something more powerful than just SQL to discuss it. So we need relational algebra for that. So in this course, the way I'm going to handle this is we're going to learn them in parallel, because I know that diving right into just talking about theoretical stuff, just relational algebra, can be a bit tough, because why would you need a certain thing? Why would you model it this way? Talking just about SQL can be tough because you get a limited view of the world. So we'll talk about them both at once. So the first operator I want to define, a brand new operator, is, I'm going to call it pi, but its name is the projection operator. And the idea behind a projection is that we have a relation, so we've defined in this slide this sort of abstract relation on n columns, a1, a2, an. And the goal of projection is to reduce, or, well, we don't have to reduce. We can have a projection that keeps everything. But the projection operator allows you to decide which columns you want to keep. So notice that I'm using the operator sort of in a functional style. So I write, pi of r. And what comes out of pi, so this quantity, is itself a relation. And the goal of the projection operator is I have some set of columns in my original relation. I want to filter some of them out. And in my earlier example, here I might say that I have my products table. I would like a brand new relation that contains only these two columns, product ID and name. What I'm doing, therefore, is I'm taking a projection of the products table. I am excluding certain columns from my result. So the projection operator in this case, what I would probably write is pi of, and as a subscript to the pi operator, you list the columns you want to keep. So I say I want product ID and I want name. And then then the argument to the operator is the products table. So this, I've done a projection, and what I get would be what I've circled up there. A new relation which gives me, whose attributes are product ID and name. And so what this is defining formally is you have a relation that has n columns, and you specify some subset of them. These columns B1, B2, BK, so each BI is equal to one of the A's. They could be in a different order, but it's some subset of the existing columns, and the result is every row of the original relation, but only those columns that you specified. Notice that, and this is going to be true of all of these things, because the pi operator is taking relations to relations, the output is a relation, it can't contain duplicates. And you'll notice in this case that's never going to happen anyway if the input doesn't contain duplicates. The pi operator doesn't add any new tuples to the relation. It just modifies the ones that are there, or we shouldn't say modify. It filters them and creates new ones based on filtering them. We will notice, and this is actually not for, we don't want to have duplicates in our relations. We'll notice that SQL operators don't remove duplicates unless we tell them to in most cases. That actually isn't a bad thing, because there are times in SQL where it takes us a few stages to do something that might only take one relational algebra operator. And in those intervening stages, we can't lose the duplicates because we might need them later to do things like count how many of them there were. So here's a projection of that products table. Here I've taken name and price per kilogram. And just to note about this, if I had specified these in the opposite order, so pi, price per kilogram, comma, name, I would get my result with the columns in the opposite order. Price per kilogram first, then name. So you can actually use the projection operator even with every column just to reorder the columns if you want to. And here is an example of the projection of order contents taking only order number. Now this is a place where duplicates do have to be eliminated, because although the order contents table, and You can see why I recommended earlier that you just pull this slide up on the side. I guess I can't do that. I have to wave my hands and draw all over things. If I take the order contents table and project just this as a relation, well, if I'm only looking at order number by itself, if I'm ignoring all this stuff, then I do have duplicates in the result. I've got these three are all the same, so are these, so are these. The pi operator gives me a relation. So what it gives me is the set of all order numbers, and it gets rid of all the duplicates because I'm not allowed to have duplicates in a relation. And so if I take a look at the projection that I end up with, we can see it's just a list of all the order numbers in the order contents table. So that's one thing to consider. It's one trap to avoid falling into when you're writing a midterm or something. Just because we're doing a projection or whatever doesn't mean we don't get rid of duplicates, or we have to evaluate the result and then pull out any duplicates that occur. There may not be duplicates in the input, and maybe there aren't any in the output, but if they are, we have to throw them out. Here's an example of achieving the same thing. So here is the projection from earlier, name price per kilogram off of the products table. I can do that in SQL. You might notice it's not as obvious that, like, maybe you've seen SQL before. It doesn't seem like we need to give a name to this. We're not saying projection or pi anywhere. When I specify a list of columns in this first clause of my select statement, I am doing a projection. I'm asking for specific columns to come out of my input table. We'll also notice that SQL does not by default remove the duplicates like I just indicated. You can tell it to do that. You can tell it to enforce a strict projection, a relational projection, but if you don't, it will let the duplicates stay in. It will just strip off the columns you didn't ask for and then give you the result. Oh, the slides agree with me on that. I guess I'm talking ahead of myself. So the standard select statement, if I just give the column name, if I say select order num, then I'm going to get this. And this is not actually the formal result of the projection operator. This is the result of select stripping off those extra columns that were there, and that's it. What I am allowed to do is stick this keyword, select distinct. And for our purposes, for the time being, we'll notice that SQL has a very odd grammar. But for the time being, what I'm saying is we can sort of call this the select distinct statement, in a sense. It's still a select statement, but we put the word distinct before all of the column names. And what this does is it does the projection as it would before, and then goes through and weeds out all the duplicates somehow. It doesn't have to weed out only the additional occurrences, but it guarantees when you're done, you only have one instance of each row. So after stripping off the columns you didn't ask for, it then makes sure that the tuples that remain are distinct. Now, one of the reasons why although I just said this doesn't seem to comply with the normal way relational algebra and the relational model works, one of the reasons why it's good to have this is that there are times when, practicality has to have some bearing on things. And yeah, sure, you probably want the things to be distinct when you're done. But what if you're doing a query as part of a series of, tons and tons of other queries? You might notice it's pretty damn easy to get this result. If I say go to order contents, pull out just the elements of that one column, that's just one loop, and you're just emitting, you're just pulling out one column each. If I say select distinct, you have to do something to eliminate those duplicates, and they may not be in sorted order, so it might not be as easy to do as it looks in this case. So select distinct has a processing cost that we may not always want to pay. So the ability to turn off the strict relational interpretation is useful. Although, to be clear, for our purposes, it's not the pi operator unless the result has no duplicates. And so, yeah, we'll notice really what's happening, what I mentioned earlier about how SQL doesn't really obey the relational model in certain cases. It's pretty well defined when it doesn't, and it's usually because whatever the relational model would require might have a performance cost that we don't always want to pay. And so, although we should try and maintain strict relational modeling, there are reasons, and we'll see them pretty quickly, there are reasons why we could disable it, maybe not select distinct at first, and then later on in a nested query or something, then we boil things down. So our next operator, the one that we're going to spend quite a bit more time on, obviously, because the pi operator is a nice, easy introduction, but it doesn't do something terribly exciting, is what's called the selection operator. So this is the Greek letter lowercase sigma. I'm going to keep calling this sigma, so apologies in advance. I mean selection when I say sigma. The selection operator, we provide some conditional expression. And so in this case, I'll write one in, but in the subscript, and maybe you're noticing there's something weird. Why do I have both a parameter here and a parameter here? This is a standard way of writing mathematical notation, but the idea is that the parameter c is baked in. So it's something that we set in advance, it's fixed. Whereas this, the contents of R, is dynamic. It's something that we don't know until we have it. So in a sense, what I'm doing is I'm making my own custom version of the sigma operator every time I define it. But what I feed in, the relation I feed in, of course, I don't know what's in there, because the whole point of doing this operation is that I don't know what's in my data. I want to query my data. So I could write something like, find me all of the products whose price per kilogram is greater than or equal to 5. And then I give it as my argument that products table. So this is my condition C. So what happens when I use the sigma or selection operator is we take a look at every tuple in my relation R. And this is a good time to remember that, yep, when I listed the contents of my tables, they were in some order. There is no requirement that I go through them in any particular order to get this result. We know that a set has no internal ordering, so I can go through them in any order I want. The sigma operator is supposed to go through every tuple and keep only those that meet the condition. So only those in this case, for example, where price per kilogram is greater than or equal to 5. And the sigma operator makes no modification to the number of columns. Every tuple that meets the criteria does come back in the result. So the result of the sigma operator is a new relation with the same schema as the input. So in this case, if I start with a schema R with columns A1, A2 up to AN, when I'm done, the result will have columns A1, A2 up to AN. And so the result formally is I evaluate this condition C on each tuple, and every tuple for which it evaluates to true goes into the result. Everything else it is tossed out. And again, this, like every other relational algebra operator, takes a relation to a relation. The result of sigma is a relation and therefore will not contain duplicate rows. Now, unlike before, it's pretty hard to, you might notice, the rows I get out of this are a subset of the rows that went in. So unless there were somehow duplicates in what came in, I won't expect to see duplicates in what comes out. So another thing we have to understand is that this condition that I'm stating is a condition that can only be stated in terms of a single tuple. So I'm not allowed to ask questions about all products in my example from earlier. What I'm allowed to use in my conditional expression are only things that I could apply in a vacuum to a single row of the table. I have no guarantee about which rows will come in first or whatever, and I'm not allowed to do anything that requires remembering the result of a previous row's query. Just a condition that can be applied independently to every single row. And so in this case, I apply it individually, and then I just, in this case, I guess I'm keeping every row where the value of A is greater than or equal to the number 6. When we talk about relational algebra, so I'm getting at this point here. When we talk about relational algebra, we're going to, like we do in many other mathematical contexts, we're going to assume the honor system for types, which is that if I write something like A is greater than or equal to 6, I am implying by writing that whatever A is supposed to be is something that I can compare logically to 6. So we don't bother having to say A is an int, because we assume if we're describing these things mathematically that that's an assertion that I'm making by doing this. It's implied. In SQL, obviously, you have typed columns, and so if you try to compare a string column to an int, the database engine either has a way of doing that, so it's a well-defined option for what to do, or it gives you an error because it doesn't know what you mean. We are allowed to nest relational algebra operators the same way that I can write something like take the union of R and S and then the intersection of that with T. I can obviously, this is a set and this is a set, so I'm allowed to take the intersection of two sets. The same way that this is a relation, but so is this. The result of a selection is a relation, which means I can apply that as the argument to another selection operator. And similarly, if I wanted to, I could have, here's a pi operator, and here's a sigma operator, and here's another pi operator, and here's my relation R. Because what comes out is a relation, I can nest the operators in whatever order I want. And that's really significant. And that's one reason that it's important that we think about this as just a bunch of operations on sets. Because what goes in is a set, what comes out is a set. What this slide is observing is that you might notice that what's happening if I say, start with my relation R, keep all the rows where b is less than or equal to 10. Okay, now take the result, keep all the rows where a is greater than or equal to 6. Every row that comes out of the whole thing has to have a greater than or equal to 6 and b less than or equal to 10. And so we could rewrite that using the logical AND operator, which SQL has, like this. So the condition here is this entire thing. So I am allowed to do that. It isn't as easy to see. A nested selection does not translate into logical OR, though, for maybe obvious reasons. But it's worth considering that there are cases where the nested selection can be boiled down into one big selection. This is not as obvious if you look at the way selection works inside of SQL. And that's one reason why later in the course, the only way that we can really model when a query can be optimized is by using a higher level representation like relational algebra, as opposed to trying to just stare at SQL queries until some details fall out of them. It's also really interesting to consider the similarity of this logical AND operator and other set operations that we've already seen. And the reason why I think it's interesting isn't necessarily just as an excuse to drag the intersection and union operators in. It's because this means we don't actually have to define what AND means. We can just say AND is equivalent to this construction here. So just to run through what I'm actually saying. So this is the thing from the previous slide. This is, take everything out of R. If the tuple has both a greater than or equal to 6, so column A, and column B less than or equal to 10, then keep it, otherwise throw it away. What I want, therefore, is every tuple that has a greater than or equal to 6 and b less than or equal to 10. So what I could do is I could say, let's just compute the set of all tuples where a is greater than or equal to 6, and the set of all tuples where b is less than or equal to 10. Anything that's in both sets must have both of those conditions. And so really, it's the same to use this logical AND operator as it would be to use the set intersection operator. And so we can already see some similarities or some ways in which our operators, we've seen so far projection and selection, can fit in pretty well to our existing hierarchy of set operations. Same is true with logical OR. So I want every tuple that has either a greater than or equal to 6 or b less than or equal to 10. So what I could do is compute everything with the first condition holding and everything with the second condition. Any tuple in either of those two should be in my result. And remember that because these are all set operations, there's no worry about, what about a tuple that happens to be in both of them? Wouldn't it appear twice? Nope, can't. It's a relation. There are no duplicates. So here's an example of a selection. This is price per kilogram less than or equal to 6. And here's an example of two operators combined together. So the slides, as usual, are a bit behind what I'm talking about. I already gave that point away. Because these are all operators that go from sets to sets, I can combine them in whatever order I want. It is significant that there are rules on the order that I can place operators, but in general, you can stick selections inside of projections or projections inside of selections. In this particular case, I actually can swap these two exact operators. I can put sigma, like, so my point here, it's maybe I'm not vocalizing it effectively. My point is there's no constraint whether I'm allowed to have pi sigma or sigma pi. Both of those are fine. I can combine them in any order. Now there are constraints on where I can put operators, and they're dictated by the circumstances. So here I've got first filter the products table and keep only the rows with price less than or equal to 6. Now take the result and pull out only the name and price column. If I wanted to, I could just as easily do that in reverse order. Take the products table, yank out name and price, now go through what I end up with, and keep only those tuples where price is less than 6. So I am allowed to change the order in this case of these two particular operators. The question then is, okay, so I just said you can have a sigma inside a pi inside a sigma. Can I always swap them? Now, in an in-person lecture, this is where I would allow myself 30 seconds to a minute of awkward silence while I wait for somebody in the audience to answer, and then I get a good excuse to hydrate or something. I probably am just going to take some awkward silence while I hydrate, though. Well, that's refreshing. But there's nobody in the audience, so I'm going to just have to answer this one myself. So no. The problem is there are times when the result the operators actually can't be used. So it's not only that the result is affected, there are times where you can't produce a result. And so one example would be, I guess I can use this slide sort of as a basis, but what if I'm actually asking, so what if my ultimate goal is, give me the name of every product whose price is less than 6? So that means I would want something like this. So I'm gonna clear this out. What I'm asking you for is find all the products whose price is less than 6. That's this, but all I want is the name. So I want you to give me only one column. So how would I write a query for that in relational algebra? Well, first I would say, go grab me all the products whose price is less than 6, and then give me only the name column. So project out the name column only. So what I have here, this doctored query that I've produced, this gives me the name of every product whose price is less than 6. Now think about what would happen if I swap these two operators. So that would be this. So what comes out of this thing is a list of names. The only column in the result of the pi operator is name. And how am I allowed to search for price if there is no price column? So here I can't reverse the order of these operators if I'm projecting out a column that I need later. So in this case, so the answer to the question is no for that reason. That the pi operator could cost me some information. It could lose some information that I need on the sigma, or vice versa in some cases. Or, well, the sigma operator, I don't think will delete any columns, but in general with other operators, whether it's sigma or not, putting the sigma on one side or the other can have different effects. And so I'm not always allowed to swap the orders of operators, but there's nothing in general that prevents me from putting a pi operator inside a sigma or vice versa. And so we should be aware of that obviously just because I can always put a pi inside a sigma, or that I can always use sigma operators on data, doesn't mean that literally any sigma operator I could think up always works. There are the obvious restrictions. I'm only allowed to search columns that actually exist. If this table doesn't have a price per kilogram column, then the sigma operator is invalid. So I think that's just we'll call that a common sense condition. So the selection or sigma operator shows up inside of SQL statements as the where clause. And the where clause will, I think it's the most expansive clause, although we'll find that some of these other clauses that we see eventually that aren't on this slide are less fun to think about. It tends to be the case that where clauses can get pretty big and pretty complicated. So the where clause is could be a single condition or a chain of other conditions, but fundamentally that is where sigma happens. And remember, the key here is that the sigma operator, when I apply it to my table, applies to each row individually. If I want to ask questions about multiple rows together, so I'm going to have to do a massive page up here. If I want to ask questions like, give me the total price of each order. Okay, there's a lot going on there. Give me the total number of products in each order. Okay, well, even that's a lot of stuff. Okay, so there's 3 products in order 1003, 1 product in order 1000, 3 products in order 1001. What about give me the total weight of each order? So that's something I can do with only one table. So how much does order number 1001 weigh? Well, I think it's 13 kilograms. I bought 10 kilograms of one thing, 2.5 of another, and 0.5 of a third thing. So it weighs 13 kilograms. Now, the issue here, so if I asked a question like, could you please tell me the number of every order that weighed at least 11 kilograms? A sigma can't help you with that. That is asking a question about rows, but it's asking a question about multiple rows at once. There isn't a single row in this table that can help me answer that question. I need to use multiple rows in some cases. So sigma applies to a single row. And that's significant as far as SQL is concerned, because if we ever need to ask questions about multiple row groups, we can't just use the where clause. That'll come up a bit later. So just to be we've already seen this in that other recorded lecture, but SQL does support our usual set of logical and comparison operators. They are, for the most part, C and Java-like, so here's less than or equal to. I mentioned before that, for whatever reason, the not equal to operator is actually supposed to be this thing. So less than, greater than. Although I think most database engines these days let you write the one you're familiar with from C++ and C and Java and things. I also mentioned in my previous recorded lecture that the equals operator is this, a single equals sign. There is no assignment statement, so there's no need for confusion there. There's no need for the double equals. So we have the usual set of comparison operators and logical operators. This will come up again. I'll actually have to post extra notes about this because I can't even talk all the way through the weird ordering of everything. But we're going to see as we introduce more and more of these clauses of select statements and the different relational algebra operators that although it's really obvious if you look at relational algebra like this, what order something's being done. So this is clearly doing the sigma first, then the pi, because we know order of operations. You have to evaluate the function's operator before you evaluate the function. An SQL query is a bit more opaque because it's a bunch of parts, and it may not be obvious which part happens first. So to be clear, this is done relatively close to the end, and in particular, it is done after the where clause. So if I look at a single SQL query with a projection clause, so name, price per kilogram, what's circled there, and a where clause, if I look at a single query with both of those, it is this. It is sigma then pi. Now, I am actually able to do pi then sigma, but I can't do it with the select statement in its natural form. So I probably have to do this. So in this case, what I'm doing here is I am performing a nested query. So I'm saying select, so do a projection, select name and price per kilogram from the relation produced by this select statement. And it's naming this as T1 is saying the columns, if I ever need to differentiate them, will be part of a notional table called T1. We don't need to do that here because there's only one table concerned and it has columns name and price per kilogram. So this is explicitly doing the where clause first because the where clause is part of this nested query, which I have to evaluate before I can evaluate the outside query. And using nested queries like this is nice, I guess, because it allows me to invert the order. So here, I'm actually doing this. So what we saw a minute ago, we had pi sigma in the natural form. This is actually also pi and sigma on the inside. So the sigma is the nested query, and the pi is happening on the outside query. Because I can split things into as many nested queries as I need to, I am able to actually do sigma and then pi. Whoops, not like that. Sigma and then pi. Because here, this is a select that just does a projection, and I can't do the outer select until I've done the inner select, so I do the projection first, and then I search the result. Now, there really is no advantage to doing either order here. I would say if you have a query like this, write it as one flat statement, let the database server figure out what to do with it. There can be cases that we'll see where you want to have some control over the order in which things are executed, because maybe if you put it in a certain order, what comes out of the innermost thing is really small, so very few rows. And you might appreciate, even without thinking about how to implement database engines, if you can prune down the number of rows you're working with early, you probably do less work later. So if you do want to do projection before selection in an SQL setting, you have to use nested queries because SQL doesn't really give you that tool out of the box. And the slides are helpfully noting, because obviously that thought question from earlier might not have been answered yet, but I already answered it this time. The slides are helpfully noting that once you've done the projection, so the products table has 3 columns, name, price per kilogram, and product ID. But this thing, my temporary table T1, the result of my nested query, does not have a product ID column. So I'm not allowed to use product ID anywhere on the outside query. Okay, so where are we now? We've talked about the basic and probably the most commonly seen operators, which are projection and selection. We'll see in the next part a few more. We've actually, these exist. The union and intersection exist. We've seen this all, we've talked about this. So, and set difference. Okay. These operators all already exist. We'll notice they have pretty obvious SQL analogs. We won't need to belabor it too much. The other ones on the slide, So the ones that we'll talk about in the next part are the row operator, which is one of the least exciting things ever. We need an operator for it, but it really isn't that exciting. This operator, which of course is very important to us, we need natural join for a lot of things. This thing, which I will call inner join typically, because that's the name of the SQL feature for it. There's actually one thing that isn't on this slide that we'll come to quite a bit later called outer join. And then this. And this operator here is, we typically refer to gamma as extended relational algebra, because you really have to tie yourself in knots to really work out how to fit it into the typical relational algebra hierarchy. And by the time we get there, we'll be ready to pivot into writing a lot of applied SQL for a while. So what's coming up in the next part and in the next bit of the course is a lot of designing queries with relational algebra and SQL in parallel. So a common question, including on exams, is here's a description of some data and something I want. Write me an SQL query for it, write me a sequence of relational algebra operations that gives that to me.